So, Avi, it's okay with you. I want to kind of gently start my introduction and welcome everybody to this very special public lecture. It's the public lecture that's giving typically in conjunction with our Board of Trustees meeting, which is just as this lecture will be virtual. And we were just discussing, I hope, for the last time. For those who perhaps are joining us for the first time, let me introduce myself. I'm Robert Dijkgraaf. I'm the director and Leon Levy professor here at the Institute for Advanced Study. And I'm very pleased to welcome you to a very special public lecture by Avi Wigderson, the Herbert H. Maas Professor in the School of Mathematics at IIS, and particularly the recipient of the 2021 Abel Prize that he got together with his friend and colleague Laszlo Lovac. We're very proud of this, of course. I'm particularly proud that in the kind of last 8 years, I've been here, 9 years I've been here, 4 of the 8 Abel Prize winners had IIS as their academic home. And I joke that now we are entitled to a free 5th one, because this is quite something. Now, Avi joined the IES faculty in 1999, after spending actually quite some time here also as a visitor and a member. And his arrival marked the formal establishment of the program in computer science and discrete mathematics, a very successful and dynamical community of researchers in pursuit of both conceptual and practical breakthroughs. And Avi has been leading this in an exemplary way. Now, I think there is a technical concept that if you have a graph, there is one node that is like maximally connective, the great connector, and that's how I think of Avi as one of these central hubs in the worldwide networks of researchers in theoretical computer science. His main research area is computational complexity, concerns the power and limitations of algorithms, and he asks questions whether creativity can be automated, can randomness speed up computation, what distributed tasks can be computed privately and securely in adversarial environments, and what are the power and limitations of communication and interaction. We think of Avi's arrival at the Institute as setting in motion the so-called second golden era of theoretical computing. The first being the period when John von Neumann headed the Institute's electronic computer project. And I feel after 50 years, IIS faculty felt, well, this computer is not going away. We better do something with it. And I feel that Avi is really has been able to step in these very large shoes of John von Neumann and give this incredible amount of energy to our program. Before he joined IIS, he had academic appointments, among others, at Berkeley, at Princeton, and Hebrew University. Avi received his bachelor degree in computer science from the Technion in Israel, and then his master and PhD degrees in computer science from Princeton University. He's the recipient of many, many awards, even before the Abel Prize, the Nevanlinna Prize, the Conan Prize, the Gödel Prize, the Donald Knuth Prize. So I think you have your full cabinet of medals, Avi. No, it's interesting to note that the Abel Prize awarded to Avi and Laszlo Lovac was interesting also because it was basically the first recognizing the foundational contributions, as the quotation says, to theoretical computer science and discrete mathematics, and the role that Avi and Laszlo led in shaping these central fields to modern math. And so I think it also has, the award has a symbolic value of recognizing the important part, I would say, of the computational lens, as Avi likes to say, on all of life, but particularly in mathematics. Now, today's lecture, I think Avi will exposit the remarkable power of Alan Turing's so-called imitation game, test for probing the nature of intelligence. And I can't think of a better person to lead us into this absolutely fascinating world than Avi. And so I hope you all join us. One, in again, congratulating Avi on this very well-deserved and great honor. And secondly, to the screen, unfortunately, I have to say, and Avi, share your thoughts. Warm welcome to Avi.
Yeah, thank you very much, Robert, for this introduction. And of course, I'm really glad to be here, and thank you all for coming. Let me share my screen to make sure everything works. Let me start. I want to tell you about imitation games, which are a paradigm, as Robert said, for the Turing introduced for defining concepts. The plan of the talk is very simple. I want to introduce Turing's work, the original imitation game where he wanted to define intelligence. And you'll see the main idea, and we'll talk about generalizations and maybe speculate a bit. But the main part of the talk is going to be about modern imitation games, mainly within computational complexity and discrete math. There'll be 4 of them, 4 topics that are very important, and I'll have to condense them to just explaining the role of the imitation game in them. Cryptography, randomness, then discrete math, and finally privacy. And we'll see the definitions and the major consequences they had. And then we'll conclude. So let's start. I guess we'll delay all questions to the end. We are talking about Turing's work, so let me just give you a very brief introduction to the short and life of this absolutely brilliant, one of the greatest scientists and thinkers of the 20th century. Some of the things he did as a graduate student in one paper in 1936, by defining an algorithm, he created at the same time the science of computing and ignited the computing revolution. During World War II, he was a major player in breaking the Enigma code of the Germans and probably shortening World War II and saving, lots of lives this way. If you know how much he was interested in biology and biological modeling, but one of the most quoted papers in biology ever is Alan Turing's work on morphogenesis. And I want to talk about his work on intelligence, one aspect of his work on intelligence, and that's the imitation game. So it's just wonderful. You should try it. I recommend to everybody to read Turing's papers because of his eloquence. He starts his paper titled Computing Machinery and Intelligence by saying, look, I propose to study the question, can machines think? And he then says, well, one way I can do it is just define these terms, machine and think, like the philosophical approach. And he says, but you'll start arguing with me about the meaning I gave to them. And instead, let me do the following. Let's just test whether machines can think. And that's the approach we'll take throughout this talk. It's a behavioral approach, if you will. So let's see what it does. We have some program, a robot or a program that we want to, or somebody claims is intelligent. And one way we can test it is have some referee. In his case, he proposes a human referee that will interact in one of 2 worlds. They don't know which world they are on, the left or on the right. The right is a robot, the left is a person. They can ask arbitrary questions, and at the end of the conversation, they just declare something. They believe it, a human or a robot. We want to say that this robot is successful, maybe intelligent is a placeholder for something else, like, able to converse like a human or whatever you want. If in both worlds, the referee will behave in the same way. Of course, if the referee says human here and robot here, we say the robot failed. But I want to stress, and Turing suggests already, that it doesn't have to be a binary decision. Maybe interacting several times, we take averages, or maybe there is some confidence level to the referee, and they, in the left side, they say it's human with 92% probability, and in the right, they say 93. That's pretty close. So we want to say that if the robot manages to get a close vote as a human, whatever it is, then we say that it succeeds. Of course, different referees, we want to subject the robot to different referees. They may have different scores or different confidences, but as long as it's similar, we want to say that, there was success. And so the definition is that, we have some numbers, confidence level P0 on the left and P1 on the right. And we say that the robot is intelligent or passes the test if for every human referee, the two numbers are close. And this will be the template for us. We'll test something, we'll test some property, like intelligence, of a particular entity, in this case, a given program or robot. And we want the behavior to be similar. I will not define how similar in this talk. Of course, you have to quantify it in different settings. But we'll see this picture again and again and again as a definitional tool for different notions. This can be generalized from intelligence, and here is the sort of maybe the speculative part. I decided to put it in the beginning rather than the end. Intelligence is a tough thing to define, and of course there are lots of arguments about and mountains of papers about Turing's paper, and you can go for even more complex notions or properties. You can ask whether a computer can feel empathy or pain or fear or other emotions, or can behave as if it is or it can feel conscious or self-aware. And I think the basic message here is about this type of definition is that asking this about the computer for any one of you is the same as asking it about me or about my dog. In other words, what you really want to test is whether a computer can behave as if it feels, these emotions or these cognitive properties. Because, I must say, there's no way for me to really find out whether another person, definitely not on Zoom, is, carbon-based or a silicon-based machine. So the idea is to not go, at least in this case, not go into definitions that are about the nature of things, ontological, which may not be testable, may not be falsifiable, may not have a universal meaning, and rather go for subjective or behavioral definitions like the imitation game that give, as we'll see, in other notions, precise, testable, operational, useful, and in fact, revolutionary meanings and consequences. So this is really the main aspect of my talk, and now I want to turn to this more precise part. So we'll see these four settings that I described in theory of computation, discrete mathematics. The paradigm, as we saw, will be that two things are the same simply if they cannot be told apart by any reasonable test, and reasonable will, of course, has to, this will be the important part, defining the set of tests we subject a notion to. And I want to stress that these formal definitions are primary to everything. Once you have them, then follow wonderfully theorems and proofs and constructions and theories, and they lead to basically consequences that are, as I said, revolutionary in mathematics, science, technology, policy, and more. And these are just examples, and there are more examples which I will not give you. Okay, so let's start with them. The first one is cryptography. We'll get rid of something on my screen. Okay, thanks. Cryptography, so let me give you a really brief history of how it looked for 2 millennia. For 2 millennia, it focused on encryption. This was the main, on hiding secrets. That was, so you want to, a classical example, encrypt messages like attack or retreat in battle or other ones that you don't want anybody to break or to understand except the recipient. And there are many ways of doing it, and developed over these millennia. The classical one of Julius Caesar 2000 years ago, the simple substitution cipher, which in fact I used for the top 2 examples. Or, another substitution cipher, the Enigma machine. Here you see the famous rotors of the Enigma, which, of course, here substitution is far more complicated because sort of time dependent and message dependent. But anyway, there are lots of them. And we want to understand, when is such an encryption function good? So is it secure? In fact, the basic question is, what do we mean by secure? And people struggled with this for these millennia, and then one paper changed it all. This is a paper of Goldwasser and Micali from '81. They too were graduate students at the time. So I want to tell you how they define secure encryption using an imitation game. So suppose there are these 2 messages like attack and retreat, and they are encrypted, and we want to make sure that nobody figures out which one is which. So they said the following, in hindsight, obvious thing. Let's subject them to the most rigorous test we can. Let's allow any algorithm that runs, efficiently, that is runs in our lifetime, look at it and try to distinguish them. And we call the encryption method secure if, regardless of which 2 messages there are, are encrypted, and regardless which algorithms, which, by this quantifier, see any algorithms, any adversaries that know the encryption method and know the messages can tell them apart. They behave the same, this algorithm behaves the same whether it was an encryption of M0 or M1. Now, if you look at this, this looks like an impossibly strong definition, more or less shooting for the moon. And there are lots of things to say about it. I'll just say a few. First of all, it provides the first rigorous definition of what a secret means. And it immediately shows, none of the examples I gave on the previous slide would pass this test because, in fact, no deterministic encryption method will pass it. It's clear from the definition that if you want anything like this, it must be probabilistic. So they introduced probabilistic encryption. And in fact, they showed that it was possible to achieve this amazingly strong definition. And in fact, all you need is some very natural mathematical hardness assumption, like the factoring numbers is difficult. Yeah. And this, changed cryptography forever. Modern cryptography since then, and first of all, changed its ambitions. It suddenly stepped out of just hiding secrets to doing digital everything, shopping and contract signing and exchanging secrets and zero-knowledge proofs and elections and poker by telephone and blockchains and digital currencies, in fact, everything, where there are many participating parties. Some of them may be bad, and they still want to achieve some goals like that. So we understand today that you can do everything, every such problem. You can first of all define what it means and design protocols to achieve them digitally. So the primary question again is the definition. What does it mean that a protocol is secure? So how do you define security in such a complex setting? And I want to explain to you how it's done in one example with internet elections, but you can think about any function of many people holding secrets. And the idea is developed over some years and culminated in these papers of Yao and the paper of myself with Goldreich and Kali, that what you want in a definition is to compare an ideal situation on the left. Ideal is where you have a trusted party. Let's call the trusted party government, even though maybe it's not perfect. But at least that's how elections are held normally, right? I mean, everybody sends their secret ballots, say, the votes to the government, and the government reports a tally. This will be the ideal situation, and you compare it to the situation you want of digital elections, where there is some protocol that tells people what to do. They send messages, maybe encrypted, over the internet. And what do we want from that? Why, or when would we call it secure? Well, we call it secure if the two sides, these two worlds, look the same to anybody. For example, to any player, they don't learn more than they should on the right than on the left, for example. So more generally, any algorithm that looks at the communication of that player on the left and on the right produces a similar result as in previous definitions. And in fact, of course, we want it not just for this player, we want it for every player, and we even want it for players who misbehave, want to make sure that they cannot affect the elections better on the right-hand side than on the left-hand side. They cannot vote twice or something. And in fact, in this situation, you would like to say the same, not just for one person, but for arbitrary subsets of players. But you see the gist of it, how you would define the security, correctness, privacy of protocol in this very general setting, or in any of the settings I exemplified before. And as happened with encryption, this is just the beginning, that's the definition. But once you have this definition, it turns out that it's a very robust definition, allowing all possible algorithms is a very robust thing, and then you can develop secure protocols using various techniques that were developed that will handle any problem of the type we have seen. And again, they all rest on the same simple mathematical assumption. You don't need more assumptions for this. So somehow all of them reduce to the one assumption that was used for just encryption. And of course, there are dramatic consequences of this that we all feel and see every day in our lives. So I'm not going to go into that. So that was a cryptography story. We've seen two imitation games, and there are many similar ones that go into many other results, works, and scenarios in cryptography. Okay, I want to switch now to the second topic, which is randomness. And randomness is a favorite topic of mine, and it's a favorite topic for lots of people because everybody has ideas about randomness, what it means for them, about luck, chance, and so on. Everybody wants to understand it, physicists, statisticians, mathematicians, and it existed for eternity. And I'll tell you about what the computational complexity point of view on it says and how imitation games are relevant. And the main point is understanding what is the power of randomness. So many places we use randomness. Nature seems to supply us with perfect randomness. Nature seems benevolent in this way, and I'll denote perfect randomness by this, gold coins. It's just a collection of coin tosses that are unbiased and independent, just a perfect uniform distribution. And if you have it, then you have lots of things. There are numerous applications in sampling, in scientific experiments, in probabilistic algorithms, cryptography, game theory, gambling, and many others. And I want to highlight probabilistic algorithms, first of all, because they capture many of the others, and also because by now we understand through lots of work in algorithms that they seem to be able to do for us things that cannot be done without randomness, much, much, much faster. So we want to understand this power, and in particular, ask whether this power is real. And to start probing this, we have to understand or try to understand where are these, where do we really get these perfect random bits? I mean, are they really available? And what to do if they are not? So one hypothesizes three possible universes that we live in, okay? One which the universe has, provides us with this perfect randomness, and in fact, we can tap into it. And in this case, we get everything we saw in the previous slide. But two others that are sort of weaker assumptions about the universe is not so clear. So one is that yes, there is some unpredictability in the unpredictable phenomena in nature, maybe sunspots, stock market fluctuations, the weather, some quantum phenomena. And they're unpredictable in the sense that they seem to have some entropy in them, but they are not, unbiased, independent ones. Maybe they are biased, maybe they are dependent, like the weather tomorrow is likely to be similar to the one today. Can we use them in probabilistic algorithms? It's not clear, it's not obvious, and the obvious way doesn't work. And maybe the worst or the harshest situation is the universe actually has no randomness at all. What do we do in this case? Just what do we do with the randomized algorithms? Can we use them at all? So these are the two questions we'll probe. And I want to tell you about just one important definition, or maybe the central important definition of randomness, or what is random enough. When is a distribution like this antique coins in the second part, bias dependent bits, when will we call it random or pseudo-random? And we do it in the same way we've seen before. So that's again from papers in the early 80s of Lamicali and Yao. We want to define when is a distribution like this of this antique coins, when is it pseudo-random? When does it look like random? And by now you could have done it yourself. We subject it to every possible test that is efficient. We let any algorithm, any statistical test whatsoever, use it and produce some result. And we see what the result produced on the left with the perfect coins, and on the right with this maybe not so perfect coins. And we call this distribution on the right pseudo-random if, in all possible tests, in all possible algorithms, you get roughly the same outcome. So this is just a definition. But again, this definition, because of the generality of the tests, so in contrast to statistics, which had particular tests applied to distribution, this is basically, asks for looking random to any possible conceivable test. It allows for composition, for amplification of the proximity, for reductions, basically, between various notions. We'll see this hardest connections to computational difficulty. And it has consequences, practical consequences in cryptography and in the design of pseudo-random generators. I'll just tell you the consequences to what happened, to the theories that were derived from it to answer the question we had on the previous slide. What happens in these three worlds? So we said if the universe has perfect randomness, then we have all these applications. It turns out that with much weaker random sources, sort of very dependent biased, as long as we have some entropy, we can, use, as before, all probabilistic algorithms. The use is very sophisticated, not obvious. You just don't just plug them in. You have to do something. And this is what's called extractor theory, developed over about 2 decades, and has to do mainly with the methods, efficient methods for purifying randomness, for taking weak random sources of low entropy and just massaging them to extract the randomness in them, even though you don't know where the entropy is. That's one success story. The other success story is what do you do in deterministic? So here you have no randomness whatsoever. And here the amazing observation is that randomness or pseudo-randomness is tied to computational difficulty. We need to make an assumption here. We cannot do without assumptions because really we have no randomness. So we assume something we all believe, that P is different than NP, or in layman terms, that there are some problems that are just computationally difficult. That's all we need, and that's that seems to be generally believed. And using this quite mild assumption, you get exactly the same consequence, that you can sort of use all probabilistic algorithms known. And this is done in a different way. This uses this hardness.
Narrator dialog. OK. Button. Alt+O.
Yes, I hope you hear me because I heard somebody else. Hardness versus randomness paradigm, which allows you to build pseudo-random generators from hard-to-compute functions. So again, theory is developed over 20 or 25 years, but today we understand that every fast probabilistic algorithm can be replaced by a deterministic counterpart that's not much slower. So it sort of goes against the belief that randomness is powerful. We understand that randomness is in fact much weaker than we used to think. But anyway, we lose nothing in these 2 possible worlds that seems much weaker than the perfect randomized world. These are very elaborate theories and have many consequences beyond just the results that I put on this slide. But of course, again, I'm not going to go into them. I just want to demonstrate the importance of the definition and the form of the imitation game in it. Okay, so the next third topic I want to discuss is more in the mathematical arena. And this, as opposed to computational pseudo-randomness, we'll talk about structural pseudo-randomness. And the setting I want to choose is a setting of so-called Ramsey's theorem, which here is the meta-theorem that's implied by Ramsey's work from a century ago. That surprising statement saying that every large enough system, regardless how chaotic it looked or unstructured it looked, must have some, really nice structure within it. The famous story is about a social science study done in the 50s, previous century, by a Hungarian called Zalai and his group about friendships in classrooms, among kids, and he discovered some amazing pattern of structure, about cliques of kids that are all friends with each other, are all not friends with each other. And being in Hungary and knowing the top mathematicians at the time, Erdős and Turan and Sos, went to them and told them about this amazing discovery, and they said immediately, you didn't need to conduct this social science study. You didn't need to bother yourself. It's a mathematical theorem that you will always find this structure. So I want to talk about structures in large systems. And the first structure I want to discuss is periodic sequences in integers. Here are all the integers, and I just want to demonstrate what the periodic sequence is. So the top one is it's a sequence of length 6, where I take, you see the regular intervals. I take every fourth element, 7, 11, 15, 19, and so on. So it's one periodic sequence, and I can go on. And in the bottom, you have another sequence, 5 elements that are exactly 7 apart. Okay, so that's what the periodic sequence is. And of course, we can find it in the integers because the integers are periodic themselves. But if we look at some subset of the integers, like this one, then of course, well, they are not there. And imagine this is going on some arbitrary subset of the integers all the way to infinity, but not all of them. And the question is whether such a subset or which subsets contain long periodic sequences. Let's say a periodic sequence of length 1 million. It's not clear. It's not clear at all that which would and which wouldn't. And it is an amazing theorem of Semeredy from 75, solving a conjecture made 40 years before, that every dense subset has such long periodic sequences. By dense, I mean, let's say, take 1% of the integers. Doesn't matter which, you will always find a periodic sequence of length 1 million, in fact, of length 1 billion, or any length you like. And replace 1% by 1 fraction, 1,000th fraction, or 1 millionth fraction. It will still be true. It's an amazing theorem. Then people looking at other subsets which are even sparser than 1% or 1 million. These are here are the prime numbers. And for number theoretic reasons, you might want to know whether there are regular patterns, periodic sequences of arbitrary length in the primes. And again, there's a major theorem of Green and Tao from 15 years ago that, yeah, the answer is yes. And the question is, how do you prove, some structural result like that? And that's what I want to tell you about in the next 5 or so minutes, and about Semeredy's remarkable insight. So what he said is that, if the subset is random, then it's not hard to establish the existence of long periodic sequences. So how do you use this? Of course, the primes are not random, or there are dense subsets which are far from random. So he suggested, you may think which subsets look random. Is there a sense in which all of them do? And he says, well, let's forget about subsets for a while. Let's look at something else altogether, which in fact is more important. Let's look at what networks look random. And it turns out that he found an ingenious way of using this to take care of the arithmetic progressions or the periodic sequences, which I will not tell you about. I want to tell you about his work on networks and how the imitation game features there. So for this, I have to talk about networks, clusters, and bonds. So what's a network is just what you imagine it to be. You can many nodes connected by pairwise connections. Can be a network of roads or the networks of connections on the internet. So it can be physical, but can be virtual, like connections of friends on Facebook and so on. So imagine this is a really large one, like having 1 million or billion nodes. And now a cluster is just or a community is just a subset of the nodes. And what we want to understand, the crucial notion, is the notion of a bond between two communities. And the bond is just a number. We look at all the connections between the two communities and look at the fraction of how many there are relative to how many there could be if they were all connected. Okay, so it's some number between 0 and 1, the density of connections between these two communities. And we'll be interested in bonds between arbitrary pairs of communities that can even overlap. Okay, so that's the notion of a bond. And now crucial to everything that follows is the following definition, imitation game style, of bond similarity. We have two networks here on the left and on the right, and we want to say that they are bond similar if every two communities have roughly the same bond. So if we look at these two and we look at the same ones on the right, we see roughly the same fraction. And similarly, we look at these, and you can do it for all of them. If for all of them, so we subject them to all these tests, many tests, any two large subsets are bonded the same way, then we say that these two networks are bond similar. So this is a crucial definition. And now comes the discovery that uses this. It's what's called regularity. And that's the notion, or that's the statement that every network looks random. So I want to explain this. So here's a network. And Semmelweis regularity lemma says that every network is bond similar, looks like a random network. And what does it mean? So first of all, the way it's proved, he shows that every network has no matter how large, has a really tiny model. And if you just know the bonds between a few communities, then they determine all bonds. I just want to tell you about this tiny model and the connection to a random network. So what's a tiny model? Semmelweis regularity lemma shows that no matter what network you have, no matter how large, you can always partition it to very few communities, in this case just three, the red one, the blue one, and the green one. And you just record the bonds between every pair of them, the reds among themselves, the blue among themselves, and so on, and the reds among versus the blues. You just record it in a table. This table is the tiny model. And his claim is this captures everything you want to know up to bond similarity about this network. Put differently, he said, let's construct a random network using this template, this very tiny template, 3 by 3 matrix, or 10 by 10 if you want more accuracy. So look at the same nodes, just copy the same nodes, and now draw at random connections between the red ones according to which, in this case, we do it with bond 0.8, 80% of the connections. Between the blue ones, this is 0.3, and so on. Between the green and among the red and green, red and blue, and blue and red. And his statement is now that if you do that, what you got on the left and what you got on the right are bond similar with extremely high probability. In other words, the network on the left, which was arbitrary, looks random. And if you know that something looks random, you have a lot of power. Then you know you can infer lots of things. And this inference is what eventually gives the result also about sequences. This is one of the most important results in discrete mathematics. And not only because it resolves some original long-term open questions, but also because of the consequences. And here is what I call regularity galore, that it exists in many other places. So Semmelweis talks about graphs and or networks, and it talks about sequences that you can always make them look random. And it turns out that this is true not just for these objects, but for almost any types of objects. And not just for the tests that are bonds between communities or about periodic sequences, but practically any other set of tests. So it's a very general statement that you can make here. This evolved in mathematics in this series of works, usually under the name quasi-random graphs or transference principle, and in computer science in parallel and then together, joining forces under the name dense model theorem. And a consequence is this understanding that there is some dichotomy in a very general class of settings between structure and randomness. And once you have this dichotomy, it provides a really powerful tool to solve important open questions, not just in discrete math and number theory as we saw in complexity theory, but also in other areas in analysis, algorithmic theory, and partial differential equations. And I'm sure more are coming. There are just more and more of them created by this very paradigm that originates in this, imitation game definition of looking similar. This imitation game appears in all of these settings. You just have to set the right family of tests you subject your objects to. So it's a very powerful way of thinking. Okay, that was my third example or third topic, and I'm going now to the last one, which is privacy. Privacy, again, is something that's very dear to everybody, very important. Everybody wants to keep their privacy. And we are going to see, everybody discusses it all the time in the public sphere, in the policy making and so on. And I want to tell you, this is the most, I would say, recent development compared to the other three. I want to tell you about a notion of privacy derived again by an imitation game definition that has proven very powerful. So let me talk about the the two issues that come with, of course, it's the utility versus privacy in understanding data. So what is a setup? We have some database, D, some set of records, individual records. You can think of this as, there are numerous examples. Can be census data of the population with the information like residences and this, income and so on of people. Or it can be medical data about individuals in a particular medical test or experiment. And once you have data, you immediately have the data analysts who want to, interact with this data and figure out things about this data that hopefully will benefit humanity, which is the utility part. Maybe in the census case, you want to understand welfare gaps, urban planning, and building roads and stuff like that. And in the medical case, of course, you want to understand drug development and efficient treatments to disease and epidemics and pandemics and so on. So there are obviously good use you can put data to. So that's why we want data and data analysis. On the other hand, everybody is worried about their privacy when the data is stored and viewed by lots of entities like that. And you can think that a particular person, let's say our beloved director, is in the database. There's a consideration if it's a medical experiment, why should I participate? Maybe, some information about personal information would leak. Or if you have to participate, like in a census, why should you tell the truth? So this is an obvious trade-off, and we want to understand. In fact, since data existed in bulk, the 60s and 70s, computers and storage systems became abundant. This problem was discussed, and of course, various suggestions were made, like natural ones is restricting queries to the data, let's say only allowing aggregate queries, like what's the average salary of everybody between the ages of 30 and 50 in the East Coast or something like that. Of course, that's not enough. This can reveal private data. People suggested filtering the answers, so inflicting noise, so somehow not answering questions precisely, but noisifying them in some sense. And there are many suggestions, and I would say that generally many good ones and many were used in various situations. But there was no rigorous theory and no, no guarantees, no, principled way of using such filters until this amazing paper from about 15 years ago that suggested the notion of differential privacy. So it really addresses the question of a particular individual, say Robert Digraph, who is in the database on the left, D0, but is not in the database on the right. Or more generally, any two adjacent databases that differ only in one record. And now you want to say when is the filter, something noisifying answers is good for queries. And what you want is, just as in all the examples before, you want to say that when you ask the same query of the two databases, you get roughly the same answer. So a filter is differentially private if for any two adjacent databases, namely differing in one record, and for every query from some set of queries, what you get in both worlds is the same. Now, this is natural, of course, and is extremely powerful. This general definition allows for, as before, allows for composition. You can study what happens when you do many queries, how errors add up, what kind of accuracy you get, so what kind of the trade-off between utility and privacy becomes a mathematical relation. This definition automatically guarantees resistance to future knowledge acquisition. Like you certainly don't want that maybe a year later when Robert Digraph puts some information on his website, that it will help reveal more from these database queries. So it protects against this automatically. But, and there's a beautiful mathematical theory that I'm not going to get into, that goes into this really clever ways of enhancing accuracy versus privacy trade-off. But I would say that one impressive, sort of proof on the ground is the use of this notion, both by the government. They have decided that this is how they are going to release results of the 2020 census data, using differentially private mechanisms. And this is how, by now, most of the major companies that have huge amounts of data are releasing data for data analysis, data about, they have, as you well know, they have a lot of information about us. And some of it is valuable and is studied, and the way they release it in many cases is using uses differentially private mechanisms. So it has been extremely successful in answering the problem it was set out to answer, defining and making useful private data analysis. But I want to conclude in my last slide with an application of this idea that was totally unexpected, I think, and central to science, and has no privacy in it. So somehow studying this mathematically led to the following thing. So the last story is about adaptive data analysis. And this came out in these two papers quoted above, and then many other follow-ups. So what's the story with adaptive data analysis? What is life really like for scientists, for machine learning programs, and so on, data analysts, and so on? I mean, there is this data that, as before, we want to understand and develop some models of and use them to benefit humanity, say. And now there is no privacy issue whatsoever. Let's forget privacy. The way it evolves is, this person or system asks some queries of the data, get some answers, then reevaluate the situation, maybe tune parameters of the model, maybe form new hypotheses, and send generate more queries to the data, and then gets the answers, and it repeats again and again. Maybe different analysts are doing the same with that data. So, what's the problem? This looks great. I mean, that's what's happening in fact, humanity made lots of progress with this. So what's the problem? Well, the problem, as many scientists will tell you, and it's discussed, all the time, is that there is a crisis in science. This is just a quotation or the title of a very quoted paper. It probably has 10,000 quotations. It's called Why Most Published Research Findings Are Wrong. If you read this, it's clear that there is some crisis, and there are other papers where crisis is in the title. So there is, crisis in the statistical research and so on. So what's the crisis? Why should it be the case that research findings are wrong? And in fact, most of them. There are several reasons. I want to point out to a particular reason that has to do with the adaptivity. The main issue is the data is expensive. I mean, collecting data, especially labeled data, is expensive. Because of that, data is being reused again and again by multiple people and entities. And this causes an overfitting. As you tune parameters, you get to understand the data you have better and better. And the model, your understanding of the data, fits the data that you have, and thereby provides no generalization to what you are really after. And what are you really after? I mean, the data is not what you're interested in. Where did the data come from? Came from the world, right? Maybe it came from a population study. You are trying to understand some illness or some natural phenomena, like why did the bee population in the world went down by a factor of 2, or anything about nature. The data was collected by sampling, and what we really want to understand is what's happening in the world as opposed to what's happening in the data. So if your process of understanding tunes itself too much to the data, it will not explain what happens in the original distribution that you are sampling from. That's a serious problem, and that causes this crisis. And here's the amazing discovery in this paper, is that if you apply a differentially private filter to your data in the same way we saw before, right? Again, we don't care about privacy, but let's do it. Then it turns out that, again, it's a mathematical theorem or set of theorems showing how this can result in preventing overfitting and ensuring statistical validity and generalization of this analysis, despite the fact that we are reusing data, despite the fact that we are adaptive, and just quantify how much queries, what kind of queries you can use so that your results will generalize. So there is an amazing and unexpected consequence of the understanding of privacy to this very general scientific endeavor. Okay, so that was my last example. Let me now conclude. We saw the paradigm, the imitation game paradigm. Things are identical unless you can tell them apart. And this you can apply to anything, which you want to test whether they are real or fake, to diamonds or Picassos or to news. It's a very powerful paradigm. U is the set of tests that are available to you, or to studying whatever you. Of course, it's different for testing whether diamonds are real or fake, whether testing Picassos or testing news. The definitions of this nature, behavioral subjective definitions, like imitation games, are very powerful. And in some cases where we saw amazing consequences, they may have use for understanding many other notions, including those I talked about before. I mean, initially, that have to do more with cognition or emotions and so on. And finally, I want to say that actually, since Turing's time, the field of theory of computation has been primarily about modeling. It's a modeling science, about definitions. And these definitions are extremely tuned to understanding whatever underlying process you are studying, and in particular, its resources. So this is what Robert called in the beginning the computational lens on the sciences. And once you have these definitions, as I said in the beginning, they lead to a lot. They lead to theories and theorems in math, science, and they lead to technological breakthroughs and new policies and new products for society. So let me conclude with this and end with my favorite slide for every talk, which is in case you want to learn more about, in fact, the subjects I talked about, except the last are exposited in detail in this book, but many, many others. Elaborations of computational complexity, its interaction with mathematics and with the sciences. This book was published by Princeton University Press, but is available for free on my website, so you can all look at it. Thank you very much.
Well, thank you, Avi, for this absolutely beautiful, powerful, and wide-ranging lecture. You know, we had at some point almost 400 people participating, would never ever fit in Wolfenson Hall, and so that's one of the advantages of being online. The disadvantage is that it's very difficult to applaud. So I'm applauding you here, you know, on behalf of all of us. Thank you so much.
Thank you.
And I think now we have time to play our own imitation game. So the audience will ask questions and they figure out whether we're talking to the real Avi or some very sophisticated deep learning algorithm version of Avi that we have created in our IIS laboratories. And to play this game, you can raise your hand, you can raise the hand digitally, use the chat, or just shout. So I'll just see. It's very difficult for me to look at 7 screens at the same time. So I need some help here.
But maybe people can just unmute themselves and ask. Maybe this will work.
Unmuting is a very easy way to start.
Yes, so somebody.
Ashutosh.
Yeah, hi. Great lecture, Dr. Avi. One very naive question I wanted to ask based on the implications of some of the implications of your presentation. There is a growing concern, as you rightly pointed out, about the privacy. And there is a balance to be achieved between the data encryption that ensures the privacy and this new evolving computing power, quantum computing. So on the one hand, we are trying to encrypt the data more and more so that we can maintain the privacy. But on the other hand, we are also enhancing the computational power through the quantum computing and other methods. Where do you think this balance will tilt towards? Is it going to be ongoing tussle between encryption and computational powers, or there is any solution to it?
Yeah, so first I want to make sure that there's a distinction. The privacy you are talking about is more the cryptographic privacy I mentioned in the earlier part of the talk in the first example. Privacy at the end, the differential privacy has no cryptography in it. But your question is excellent, and the growing power of computers, and in particular the possibility that quantum computers will exist, just keep demonstrating to us this infinite cycle of war of attrition between cryptographers and cryptoanalysts, those who are trying to design cryptographic systems and those who are trying to break them. And I think this will go on. As many of you know, the possibility that quantum computers will be built, and if built, they can factor integers, and this will completely demolish current security systems. There's an effort to create quantum resilient cryptography. In fact, there is one variant of or one class of cryptographic methods that are based on lattice problems, and as far as we know, are not breakable by quantum computers, but of course were not implemented yet. So if we need, people are working on trying to make them practical. I think it will be a big disaster if quantum computers appear tomorrow, or even if they don't, if somebody finds a factoring algorithm, classical one tomorrow, because to do this replacement will take many months, and it's not clear to me what will happen to the economy during these months, to banks, to governments, to exchanges. But well, it didn't happen, and I think that there is some work to try to find replacements. But yes, to your question, I think this war or this struggle between cryptographers, cryptoanalysts will always continue.
Thank you so much.
Yeah, many
Question
questions.
for Professor Sherris Thompson. Sherris.
Thank you for this wonderful talk. I'm speaking as a non-mathematician now. I just had a question. For many other realms of life, what really matters about the fungibility or non-fungibility of certain things is the provenance and procurement, the way in which something is got at and where it comes from, rather than anything about the content of the token itself. Is there a mathematical equivalent to that? And is it helpful to you or unhelpful? Bad for privacy, good for privacy?
I think that it's a great question, and I think the same standards can be applied to the methods of procuring the information than to using it. And yeah, it's something to study. I can't think of just telling you a name of a mathematical theory that applies to this, but people do care mainly about the cost of obtaining reliable information, and before using it. So yeah, it's I think this paradigm is very general and can be applied in lots of situations. I'm not suggesting that this is a universal thing, that is the only thing on earth. I mean, just wanted to demonstrate the importance of this paradigm to lots of things that were already very impressive. Yeah.
Thank you. Ian Yaslan.
Thank you. Thank you very much for this really lovely talk. I had a question that's related to one that was asked earlier, which is that you explained that these imitation games, they're based on this idea of using an efficient algorithm to tell apart between two different things. What happens if quantum computers come in and change the paradigm for what is efficient and what is not efficient, and how much does that change the picture of what you just explained today?
You just replace efficient algorithms by efficient quantum algorithms. That's what you do. I mean, you apply, all in cryptography and randomness, you would apply the most powerful things that are available. But you have to remember that this availability of quantum computing will be available also to the cryptographers. So maybe there are ways to devise quantum encryption methods that will be resilient to quantum attacks. So yeah, this, as I said, this fight will continue. But you always, I mean, in different situations, you want to apply the appropriate set of tests. For cryptography, I think you want to apply the most rigorous set of attacks, and we saw that it also helps solving problems, not just makes things harder. Yeah.
Thank you. Question by Paul Borkard. Unmute, Paul, please.
Hi, Avi. Thanks very much for the talk. I just want to attest to what you're talking about with the differential privacy being so useful. Definitely, like the use in sort of machine learning is very important. One thing that we've done is looked at the privacy versus utility trade-off. And normally the differential privacy is done by adding, randomness to the query. What we've looked at is using randomness in the data itself to provide part of the randomness that you use, and then you can often improve the utility because you had to add less artificial randomness. So that's something that has helped us.
Yeah, it must have been clear, these are vast areas, all 4 of them, and I gave 10 minutes to each. So there are numerous things I could not talk about, and I focused on the definitional part that led or was the important part of the series. But thanks, yes. It's very important to minimize the use of randomness in all applications because it's a costly resource.
Great. Joel Spencer.
Joel.
Yeah, unmute, please. Or perhaps, yes.
Thank you very much, Avi, for a wonderful talk. If I can get back to regularity galore, and you speak about dense. Well, a lot of things like the Facebook graph are not dense. Do you see a possibility to extending this to other cases, non-dense structures?
Yeah, not only do I see a possibility, it was done. There are parallel studies of sparse regularity lemmas, both for graphs and for other structures. It's more complicated. Actually, the Benjamin Ishram, for example, work on sparse graphs. It depends how sparse you can apply. There's a variety of results for sparse objects, definitely sparse graphs, and there are, I would say, similar in spirit, although not similar in strength, results about sparse graphs and other sparse objects. Yes.
Okay, thank you.
Just looking around. Any other questions? Yes, Ari Shaviv.
Thank you for the wonderful talk. So your remark about, well, if we'll have quantum computers and the people that build the algorithms can use them, not just the people who try to break the algorithms, is very interesting, I would say. And I wonder if you can say something general about this kind of trade of assuming the definition of difficult is the same for the one that wants to construct an algorithm and for the one that wants to break it. Can you always build something that is secure, let's say?
Yeah, it's a very good question, and it's not obvious at all. So a primary primitive underlying cryptography is the notion of one-way function. Is a function that can be computed in one direction, but it's hard to invert. Easy and harder is, like to say, for the same type of power, whatever it is. In classical computation, we have plenty of examples for that. In quantum computation, it's not so easy to do because quantum computing is reversible. So you have to think of alternative notions. So your question is very non-trivial, and I don't know of a general theorem that says, for any fixed computational power or computational model, you can always have something like that that will underlie cryptography. It's a very good question.
Thank you. Another question by Hiralal Janma.
Yeah, good afternoon. I think the RSA crypto system, I was told by an expert, I don't want to give the name, would not be accepted as a rigorous crypto system. how do you go about designing crypto system? For example, say Lattice or MacLeese or other crypto system for quantum computers. I mean, can you shed a light on that? I mean, one is actually very abstract, rigorous proof for security, and other is actually practical crypto systems.
Right. So for all of the crypto systems, those in existence and those theoretical, first of all, you want to at least it's an ideal to base them on some clear, well-defined mathematical problem. And of course, later making it practical is another issue that the practical people are doing. And in fact, I don't know what you meant by RSA is not a valid cryptographic system. Lots of the world's security systems are still based on RSA or RSA-like.
Sorry, go ahead.
Well, it doesn't matter, but anyway, you are using it. You are using it when you're shopping online. You should know that. And right. So, but anyway, if you ask about the more modern or the quantum resistant suggestions for quantum resistant cryptography, these lattice-based systems, the idea, I mean, for those who know what a lattice is, I will not make it long, a regular pattern in high-dimensional space. The kind of problem that is apparently hard is that I give you some basis of the lattice, and you ask what is the length, approximate the length of the shortest vector in the lattice. This is the type of problem that is believed hard, and not only believed hard by through ingenious work of Miklos Aitai, is hard on average, which is really what we want for a cryptographic system. We want it, when you generate your password at random, we want that it will be protected, not just some particular password. A very particular one would be hard to break, but most of them would. So anyway, the underlying computational problem is given a basis to a lattice compute or approximate the length of the shortest one. And that's this. You can base cryptography on this, first by Aitai and Dwork, and there are other suggestions by Regev and so on. And people are just trying to make them practical, making them usable large scale, and companies are on it. NSF is supporting it big time, and so on.
Thank you. Perhaps a last question by Walter Fontana.
Hi, you said, if I correctly remember, that so in connection with Ramsey theory, that a sufficiently large object, graph, a set, or whatever contains some order, regularity, a structure. So containing is good, but can I find it?
This is really just a fantastic question, not just fantastic in general, but fantastic talks to my heart, because this is the type of problems that we look at in the complexity theory or the theory of computation for any mathematical theorem. Stating that an object exists, we immediately, and by now as a gut reaction, ask, can we find it efficiently? There are many existence arguments in mathematics that are not constructive, and trying to get them constructively often leads to more and better knowledge and understanding of whatever objects there are. So it turns out that in many of these cases, the answer is yes. In many, including the very general statements I made in the regularity galore picture, in particular for semi-ready regularity of graphs, finding this regular partition, this tiny model efficiently from the network. There's a paper by Alon, Duke, and a couple of other people finding it in polynomial time. And there are similar results regarding other objects, but it's not universal. I think the problem is of efficiently finding these structures is just a great question, and sometimes we don't know it, and even when we know it, exactly how, once you start getting into the actual parameters of, how regular are they, or how large is the structure you find, it becomes more complicated. So this is a great collection of algorithmic questions right in there. Thanks.
Well, thank you so much, Avi. I think if I'm the judge, I think we have been talking to the real Avi. You passed the test. I
take it as a compliment.
You should take it as a compliment, and it seemed to be hard to think of any question that you do not have an answer to. And we're so happy that you gave this talk. I would say we had a sellout Zoom screen. And thank you all for joining us. And again, Avi, thanks for everything you have been doing for the Institute, for the community, and this great and much deserved honor of the Abel Prize. And we'll be cheering that at another occasion. But thank you all for joining. It was absolutely wonderful to see you.